Hello everyone, my name is Sebastian Böcker and this is a talk about COSMIC. It will be extremely incomplete, but at least it's very short. So the general idea is very similar to what we do in spectral library search. When we look at the different spectra in our library, we do not only sort them by the cosine score similarity to our query spectrum, but in the end we also look at the hit, the best scoring library spectrum. And if the cosine score is close to 1, we would rather believe that this is a correct hit. And if it's close to 0, then it's probably incorrect. So implicitly, we sort them by score. Now, a rather obvious question is, can we do the same for in silico tools, which do not search in spectral libraries, but in structure databases? Because there the problem is our structure databases are many orders of magnitude larger than the spectral libraries. So we often get an answer simply because something is most similar to our query, but that doesn't necessarily mean it's correct. Can we decide if it is correct based on the score? And the short answer is no, this does not work. I'm not going into the details, but here are different levels of false discovery rates, exact FDR. So what are you accepting for your answers? Like 5% of your answers are incorrect. And then how many answers do you get returned? And you see here all the methods. And if we sort hits by score, they all return practically nothing. So we first considered score calibration, something that has been very successfully used in proteomics. And what you try to derive is no longer just the score that an in silico tool gives a hit, but instead you try to estimate the p-value or the e-value of how likely it is that this happens just by chance, because everything can happen with a certain probability just by chance. So what we saw when we looked at the CSI finger ID scores was that they sometimes looked like a log normal distribution. So we used that in our modeling, but also that often these score distributions were multimodal, and that didn't allow us to use one parameterized distribution. So instead, what we use is a kernel density estimate. So this worked a little bit, but not really well. So the line here is CSI finger ID. And then if we calibrate scores, it gets a little bit better. So I'm not going to explain in detail what these curves are. These are ROC curves, but the further up here the curve is, the better are your results. So the bottom line, it's not working particularly well. So we introduced a confidence score. And if you have heard one of the CSI finger ID talks or even the Canopus talk, you have seen my voodoo chicken, which are replacement for machine learning. And so what we use here is we train a voodoo chicken, which looks at a hit, which means it's a mass spectrum plus a structure that was annotated, so the best scoring structure. And then you have information about this thing. So we have a long list of information. And then this chicken, or in fact machine learning, tries to decide if it's correct or not. And because we didn't want to get into the trouble with overfitting, we used a very simple linear classifier for that. And in fact, that worked almost perfectly, almost too perfectly. We already presented this slide 2016, and then we thought we are done. And then it turned out not to be true. And when we applied it to biological data, it didn't work at all. Now, one nice thing about using a linear classifier is that it's just a linear combination of the input features, so you can really check what feature is responsible for what. And doing so, we noticed something strange. For example, we noticed that fragmentation tree score, the higher the fragmentation tree score, the worse our confidence in a hit was. And that is really strange, because Sirius instead selects the best fragmentation tree based on the highest score. Okay, so high fragmentation tree scores are simultaneously good and bad, and that doesn't make any sense. So what we used to get around that was we decided upfront if a feature was good or bad for our confidence, and we enforced that when training the machine learning model. And with that, results actually get worse. As I said, I'm not going into the details here, but the further to the upper left corner here you get, the better is your classifier working. And the unrestricted one, where we didn't impose these restrictions, actually works slightly better, or not so slightly better. I would take it. But the important point is that it doesn't really perform much better in the most important region. I'm not going to explain why this is the most important region, but actually this is the only part of the plot that should really matter for us. So this is now showing that indeed the new confidence score works much better, separates much better than the original CSI finger ID score as well as the calibrated score. And we tested that for different data sets, for cross-validation data, for independent data, for different fragmentation energies, and so on and so on. And the results are mostly always the same. It always works. Another data set, this time the CASMI 2016 data set, now the comparison with the other methods. And indeed, the cosmic confidence score is able to return reasonable number of hits at very low false discovery rate. And another independent data set. And again, it works. This one is funny because here the original CSI finger ID works worse than random. In fact, we can better separate than if you would do spectral library search. I'm really not going into the details here because I have noticed that a lot of people get upset about that. So if you don't believe me, that's okay for me as well. But all the numbers are indicating that yes, Cosmic and the confidence score work better than spectral library search. So we also use that to actually detect something interesting, biologically interesting. In fact, we annotated 11 novel bile acid conjugates. What we did there, we first combinatorially generated more than 28,000 bile acid conjugate structures. That's just using a program that is able to generate such combinatorial structures. In fact, you see them all here, but probably you can't really see them. So let's zoom in. So this is with an extreme zoom. Obviously, those 28 bile acid conjugate structures are probably not present in any biological sample out there. We need a method that can now search in this combinatorial structure database, but luckily we have one. It's called Cosmic. We now use CSI finger ID to search mice fecal data set against this combinatorial database of structures. And there we found that 626 conjugate structures were annotated, but we don't know which of them are real. Luckily, we now have the confidence score and we can sort those hits based on our confidence that they are correct. Then we looked at the top 12. Why 12? Why not 12? 12 is 3 times 4, so nice to show in a figure. Anyways, we found that from these 12 hits, 11 were probably correct based on manual interpretation of the data. And for 2, luckily, we were also able to confirm them via synthetic standards. Now, before I stop, 2 words about metascores. CSI finger ID does not use any metascores. Cosmic does not use any metascores. The confidence score does not use any metascores. Metascores use, say, citation frequencies or production volumes, things like that. Obviously, we don't have that for novel structures, but I would strongly recommend not to use them even if you are searching in a regular structure database. And with that, I come to an end. Many thanks for your attention. And if you want to know more, please have a look at the behind the scenes talk.